Hello, Matthews Gatos here. Welcome to part 2 in the applications of max and mins. Before I get into doing my 2 questions, I just want to review with you my process. The way that I've simplified this process is reading the question and picking out 2 types of equation. One equation I like to call the derivative equation. So this is an equation that has the word max or min in it. So you're trying to find an optimal amount. So either a maximum or a minimum amount. That will be called our derivative equation. Now it's important to note the derivative equation can only have one variable. Now we can introduce what I call the isolating equation. So in this equation, I'm going to isolate for one of the variables so that I can make the derivative equation have only one variable. So the isolating equation is the one without the max or min. It's typically one with an answer, like an amount for a quantity. So once we've isolated for the variable, substituted it into the derivative equation, we're going to simplify our function as much as we possibly can, and then we're going to take the first derivative of the derivative equation. Once you've done that, you're going to factor the first derivative, identify your critical values that match the domain of the question. In other words, if you're talking about radius or number of people or a height measurement, all of those things can't be negative. So look at the domain restrictions within the question itself. Then use those critical values to do sign analysis to find your max or min. Always answer your question with units. So let's try our first question. In this question, we have an open top cylinder that has copper sides costing $5.40 per meter squared, a steel bottom costing $2 per meter squared. I want to find the dimensions of a 10 pi meter cubed cylinder that has the least cost. Okay, so let's look at the derivative equation. I want to find the dimensions of a cylinder that has the least cost. So that's going to be my derivative equation, a minimum cost. So my minimum cost is going to be made up of making the surface area of the cylinder, because that's the materials to make up the cylinder. So let's look at surface area of a cylinder. Surface area of a cylinder is the top and the bottom, 2 pi r squared, plus the circumference of that middle section multiplied by the height. Now, in the question, we said we had an open top, which means I don't have a top. So I'm going to just erase this 2 and say that the surface area of that cylinder is pi r squared plus 2 pi r h. Now, we're not just talking about the surface area, we're talking about the cost associated with that. So the sides cost $5.40 per meter squared. The top is steel, and that costs, sorry, the bottom, that's the bottom, costs $2. So my minimum cost is going to be 2 pi r squared. And again, that 2 is not for a top and bottom. The 2 is for the $2 of material costs, plus 5.4 times 2, which is 10.8 pi r h. So that's my derivative equation. Now you can see there's a bit of a problem there. I'm only allowed one variable, so I have r's and I have an h. So since I have 2 r's, only one h, I'm going to use my isolating equation to isolate for height. So let's go back here and see. We're given the volume. So the second equation, the isolating equation, usually has some sort of an answer. So you can see this is the answer for volume. So instead of having volume equals, I'll have 10 pi equals, and that's equal to pi r squared h. So let's cancel the pi's on both sides. So I have 10 equals r squared h. So to solve for h, I'm going to divide both sides by r squared, and that will equal to h. So my isolating equation is going to be h equals 10, and let's write that as r to the negative 2. And that will be my isolating equation. So I'm going to use that equation in my derivative equation in place of the height. So I'm going to take the height here and substitute it for here. So my derivative equation will be minimum cost is 2 pi r squared plus 10.8 pi r, and instead of h, I'm going to use 10r to the negative 2. So let's simplify this equation. I always want to simplify my derivative equation as far as I can before I take the derivative. Okay, so looking at this equation, I'm going to have minimum cost. Let's try that again. Minimum cost is 2 pi r squared plus, let's multiply these two together. So that's 108 pi, and then it's going to be r to the negative 1. So 1 plus negative 2 gives me negative 1. So looking at that, I can now take the first derivative of my minimum cost equation. So looking at this, taking the first derivative, bring the 2 down, and I have 4 pi times r plus, or actually minus, bringing the 1 down, 108 pi and r to the negative 2. So now that I've done my first derivative, I'm going to factor. So I have 4 and pi and r to the negative 2 would be my greatest common factor. 4 pi divided by 4 pi is gone. R to the 1 divided by r to the negative 2 is r cubed. Negative 108 pi divided by 4 pi is negative 27, and r to the negative 2 divided by r to the negative 2 cancels. So my minimum cost is 4 pi r to the negative 2. And then I have a difference of cubes. So that will be square root of the first term, square root of the second term, sine of the middle, square the first term, square the last term, 3r, but opposite sign. So the opposite of a negative is a positive. So altogether, my first derivative is going to be 4 pi r minus 3, r squared plus 3r plus 9, all over r squared. Okay, so we're going to look at this. We're going to find the critical values, put it on a number line to find out the radius that would give me a minimum volume, or a minimum cost, sorry. Okay, so looking at my formula here and my critical values. So here I have a critical value of r equal to 3. Here I have a restriction, so I have a critical value of 0. And this quadratic here cannot be factored. So this one here is a quadratic that opens up and it's entirely above the x-axis, so it is unfactorable, and since it's above the x-axis, this quadratic will always be positive. So let's look at our number line here. So we have our number line with our critical values of 0 and 3, so I have 1, 2, 3 intervals. But if you look at those intervals for radius, r for radius, I know that I can't have a negative radius. Radius has to be positive. So really, I only have 2 intervals to test. So let's go ahead and look at these piece by piece. So 4 pi is a constant number, and that means that it will be positive in each of those intervals. Now, r squared is also going to be positive in all my intervals because the definition of squaring a number is multiplying it by itself, so it will never be negative. And then we already established that this will always be positive as well. So look at all those things that are constant. They will always be positive. So really, the only thing that's going to determine increasing and decreasing is that factor there. So r minus 3, the factor is equal to 0 at an x-intercept of 3. So to the left of the x-intercept, the factor is negative. To the right, it's positive. So I can see here I have 1 negative, which means decreasing. I have all positive, which means increasing. If I'm decreasing to the left, increasing to the right, that tells me that there is a minimum, and that minimum occurs at r equal to 3. So to figure out the height, I'm going to go back to my isolating equation, and my isolating equation was 10 over r squared, or 10 over 3 squared, which is 10 over 9. So the dimensions to minimize the cost but still have that volume of 10 pi are going to be a radius of 3 meters and a height of 10 over 9 meters. And that would be the end of that question. Okay, let's look at our last question. This question here is going to be a minimum distance question. So looking at this question here, I want to find points on the parabola y equals 6 minus x squared that are closest to the point 0, 3. So again, I want to find a isolating equation and a derivative equation. So I want the ones that are closest to the point. That's my derivative equation. I want a minimum distance. Closest means a minimum distance. So we have to go back to our grade 10 level math to figure out the distance between 2 points. And we can do that with the distance formula. So the derivative equation is going to be the minimum distance is equal to the square root of, and I'm going to use this as point number 1 and this as point number 2. So it's going to be the difference in my x values squared plus the difference in my y values squared. So my minimum distance is going to be the square root of x squared and then plus y minus 3 all squared. So remember what I said, your derivative equation can only have one variable, and I have 2 variables here, so that's a bit of a problem. So let's look at an isolating equation to find a way to rearrange for one of my variables and substitute it in. And that isolating equation is just going to be the equation of the function, which is y equals 6 minus x squared. So any place I see a y in my derivative equation, I'm going to replace that with 6 minus x squared. So my minimum distance is going to be the square root of x squared plus 6 minus x squared minus 3 all squared. So I want to tidy up my original equation as much as I possibly can before I take the derivative of it. So the simplest form for your function will be the easier derivative. So I'm going to actually expand what's underneath here after I simplify. So 6 take away 3 is 3. So I really have 3 minus x squared all squared. So expanding, I'm going to have 9, and then I'll have minus 6x squared plus x exponent 4. So all together, let's just rearrange that. I'm going to have x exponent 4, and I have an x squared, take away a 6x squared is a negative 5x squared plus 9. So really, I have x exponent 4 minus 5x squared plus 9 all to the 1/2. And I want to then take the derivative of this function. So again, simplifying your function as far as you possibly can to make the first derivative easier. So now I'm going to take the first derivative. So the derivative of minimum distance. Bring the half down, and then I will decrease my exponent by 1, and then multiply it by the derivative of the inside, which is 4x cubed minus 10x, so a little chain rule there, okay? And now I just want to simplify this as far as I can so that I can have it in factored form to find the critical values. So in the denominator, I'm going to have x exponent 4 minus 5x squared plus 9 to the 1/2. In the numerator, I'm going to take half of these values. So half of these values would be 2x cubed minus 5x. So half of those values. And then I can factor out a common factor of x. So it's going to be x, 2x squared minus 5 all over x exponent 4 minus 5x squared plus 9 to the 1/2. And then, of course, I will factor here using a difference of squares because I want to find all the critical values. So this will be root 2x minus root 5 times root 2x plus root 5 all over x exponent 4 minus 5x squared plus 9 to the 1/2. Okay, so now that I have it fully factored, I can find the critical values and use my intervals to test. So over here is my factored form. Okay, I have a critical value here at 0, a critical value here at root 5 over root 2, and I'll just show you how I simplified that. Root 5 over root 2, I multiplied top and bottom by root 2, and that's how I get root 10 all over 2. And then, of course, you have the negative version as that as well. Okay, in the denominator, you have a square root, and that square root is always going to be positive because it's a principal square root. And you can look to see that this quadratic can't be factored, and in fact, it has no x-intercept. So I have no potential for division by 0. But you can always put that into the graphing calculator just to double check that. So these are all my critical values. I have nothing to eliminate because I'm talking about points, and points can be positive and negative. So now I'm ready to go. Okay, so let's just erase this, and we're going to look at each factor and find out whether it's positive or negative in each of these intervals. So let's start with x. So x, the factor x has an x-intercept at 0. So to the left, it's negative. To the right, it is positive. Then we have the factor root 2x minus root 5. So that is 0 at positive root 10 over 2. So to the left of that x-intercept, the factor is negative, and then to the right, it's positive. Let's do our next one. So that has an x-intercept at negative root 10 over 2. So to the left of the x-intercept, the factor is negative. To the right, it is positive. And in the denominator, as I mentioned, since that is a principal square root, always being positive in each of the intervals. Okay, so looking at these, I have 3 negatives, so I am decreasing. I have 2 positives, so I am increasing. I have a negative, which is decreasing, and all positives, which is increasing. So if I'm decreasing to the left, increasing to the right, this one here must be a minimum, and that minimum is occurring at x equals to negative root 10 over 2. If I'm increasing to the left, decreasing to the right, this is a maximum. And decreasing to the left, increasing to the right, I have a minimum at x equal to 0. So this question was looking for points that were closest to. So those would be a minimum distance. So these are the points that I am interested in, not the one that's the furthest away, the ones that are the closest. So let's figure out the y values that go with it, and I'm going to plug it into the original equation. So y equals 6 minus my x value squared. So this will be 6 minus negative root 10 squared is negative root 10 times negative root 10, which is positive root 10, all over 2 times 2, which is 4. So I have y equals to 6 minus 5 over 2. And to add these together, I can write 6 as a fraction out of 2, which is 12 out of 2. So my y value is 7 out of 2. Now that will also be the y value here, because when I square a negative, I end up getting a positive. So when I square a positive, I'll still have a positive. So both of those answers would be the same. So it will be negative root 10 over 2 and 7 over 2, and root 10 over 2 and 7 over 2. These points will be the closest points to the point 0, 3 on that parabola. And speaking of parabolas, I just want to know, what did the baby parabola drink? The baby parabola drank the quadratic formula, of course. And lucky for us, we didn't have to use that on the last question. So you guys can move along to your textbook questions. I hope this video helped, and I look forward to seeing you for the next one.